vector space and sum of vector spaces. We consider only real and complex finite dimensional vector spaces. Before going to the sum of vector spaces, we present two results concerning the relation between real and complex vector spaces. Theorem. Any complex vector space has also a structure of real vector space and any vector space, let us denote V, a vector space, and dimension of V considered as a real vector space over R is 2 times the dimension of V considered as a complex vector space. V is a vector space. This means the set V, the addition of vectors V times Cartesian product V to V for a pair of vectors X and Y is defined the sum of the addition of vectors, and the scalar multiplication in this case with complex numbers. So a map from C Cartesian product to V for any pair formed by a complex number lambda, and the vector X is defined the multiplication, the product of X multiplied by scalar lambda X. By using this, we can obtain a structure of a real vector space. We consider the same set of vectors, the same addition, V times V to V, the same as in the case of the complex vector space, but instead of multiplication with the complex number, in this case, we have multiplication with the real number of any vector. Here, a real number alpha and the vector X, multiplication alpha X R, the field of real numbers, is a subset of the field of complex numbers. Our real number alpha is the same as the complex number alpha plus 0I. So here alpha X is alpha plus 0I X, and we know how to multiply a vector by a complex number. All the axioms are satisfied, and we have a structure of a real vector space. Now let us prove this relation. For this, let B containing the vectors V1, V2 up to Vn, and dimension of V considered as complex vector space. Let B a basis of the complex vector space V. Particularly from this, we get that V is span of B. That is, V is, this set is formed by all the linear combinations lambda 1 V1 plus lambda 2 V2 plus so on plus lambda n Vn, where the coefficients lambda k are complex numbers. Now, if for each lambda, lambda k is has a real part alpha k plus beta k I, then this can be written as alpha 1 plus beta 1 I times V1 plus so on plus alpha n plus beta n I multiplied by Vn, where all alpha k, beta k are in this case real numbers. And if we this can be written as alpha 1 V1 plus beta 1 I V1, the imaginary unit, plus so on, plus alpha n Vn plus beta n I Vn with alpha k, beta k real numbers. So we get that our space V is the span. Here was the span over C, the field of complex numbers. The span over R, linear combination with real coefficients of the set V1, I V1, so on, Vn, I Vn. One can easily prove that this set of vectors is linearly independent over the field of real numbers, and here we have 2n vectors, and we can prove that these are linearly independent. That is a basis. From this, we have here a basis in the real vector space V. So the dimension of the obtained real vector space is 2 times, we have here 2n vectors, is 2 times the dimension of the complex vector space V, whose dimension is n. Here is a basis. Now another relation. If we have a real vector space, we can easily construct a corresponding complex vector space. This is a generalization of the construction of C from R is R symbolically can write in this way, and it can be identified a pair. but let us present this. If V is a real vector space, then the set we construct a corresponding complex vector space. The vectors in this case, the space of vectors is the Cartesian product V times V. That is an element is a pair of vectors from V. That is the set of all the pairs of vectors from V, X, Y, R from V. And in order to have a vector space, we have to define the addition of two such vectors, x1, y1 plus x2, y2 equals by components x1 plus x2, the first component, the second component y1 plus y2. And we have to define, in this case, the multiplication with the complex number alpha plus beta I times xy to be an element. This is formally similar to the multiplication of two complex numbers. The first component is alpha x minus beta y, and the second component is alpha y plus beta x. With the multiplication defined, this is well defined. We have V is a real vector space, so the multiplication with the real numbers of the vectors of V is defined. And this is a complex vector space, and the dimension of W, which is a complex, is the same as the dimension of V, of the starting vector space. In this case, after this construction, the dimension remains the same. One can easily prove that all of the axioms of a vector space are satisfied with the addition, vector addition and scalar multiplication defined in this way. Let us consider now we try to obtain a basis in W by starting from a basis from V. For this, let B equals V1, V2 up to Vn basis in V in this real vector space. Then the space W, which is formed by all of the pairs of vectors from V, X, Y, where X and Y are from V, equals here each X is a vector from V. We have here we write instead of X its expansion in terms of this basis. Let be alpha 1 V1 plus so on plus alpha n Vn, And similarly, the expansion of the vector y in terms of beta 1 v1 plus so on plus up to beta n vn, where alpha k, beta k are real numbers. Now, by using the addition defined here, we can write this vector in the following way: alpha 1 v1, beta 1 v1, plus so on, plus alpha n vn, beta n vn, alpha k, beta k, real numbers. And we can remark that this vector is exactly alpha 1 plus beta 1 I times v1 0. If we have this multiplication, the first component is okay, the second component also is okay, and plus similarly here, alpha n plus beta ni times vn0, where alpha n, beta n, alpha k, beta k, all are real numbers. We can denote this by lambda 1. So we have here lambda 1, v1 0, v1 0, plus so on, plus up to this is lambda n, vn 0, where lambda k are complex numbers. So W is the span over C of the set of vectors v1 0, which is from W, and up to vn 0. These are linearly independent. A linearly independent set. It is a basis in W. We can prove that this is a basis in W. So we have here the same number of vectors n, namely n, as in the starting basis of D. So the two dimensions are equal. Now we go to the sum. Well, firstly, sum of vector spaces. For this, we consider two subspaces of a vector space, and we define their sum, which is again a subspace, and will prove a formula for the dimension of the sum of the subspaces theorem. If W1 contained in V, W2 contained also in V subspaces, vector subspaces, then we get that the following subset of V v1 plus v2. We denote in this way the set of all the vectors having the form x x plus y, where x is from w1 and y is from w2. The set of all the vectors of this having this form, which can be obtained in this way. This set is a subset evidently in V. It is a subspace, vector subspace of V. Is a subspace V and dimension of this subspace is the dimension of W1 plus dimension of W2 minus dimension of the intersection of W1 and W2. Let us point A, point A, point B, point C here. W1, the intersection of W1 and W2 is a subspace of V. The order, the natural order is this one, A, B, C. So, proof. Firstly, point A, we have to prove that the intersection of two subspaces is a subspace. For this, let us consider x, y from the intersection. And alpha, beta, two scalars from the field of scalars, which here is the general case. This is the field of real numbers or the field of complex numbers. The proof is the same. From this, we get that x and y are from W1, and for alpha, beta from K, this is a subspace. From this, we know that alpha x plus beta y is in W1, and also from this, we get that x, y are at the same time W2, alpha, beta, they considered scalars, and from this we get that a linear combination. This is a subspace alpha x plus beta y, W1, W2, and from this too we get that alpha x plus beta y is an element belongs to the intersection W1 and W2. Now, point B, for the point B, we have to prove that it is a subspace. We consider let x1 plus y1 be an element of W1 plus W2. We consider a second element x2 plus y also. And alpha, beta, two scalars from the field K. And we have to prove that a linear combination alpha x times this element x1 plus y1 plus beta x2 plus y2 is also here, but this can be written as alpha x1 plus beta x2 plus alpha y1 plus beta y2. This is from W1. X1 and X2 are from W1, and this is from W2. So this belongs to W1 plus W2. So this is a subspace. Now point C. Remains to prove point C. Point C. Let B equals V1 up to Vn be W1 W1 up to the basis in W1, the intersection W1 and W2. We extend. It is a system of linearly independent vectors in W1 as well as in W2. So we can extend this system of this set of linearly independent vectors up to a basis. We extend B up to a basis B W1 by adding new vectors. That is, we have these vectors Wn, and we add other vectors in order to get a basis for W1. Let us V1 up to Vm, up to a basis in W1 and a basis in a very similar way, a basis BW2. We extend these vectors are from intersection, so they are from W2, but by adding some additional vectors, we U1 up to UK, we get a basis in W2. So the dimension of W1 of the intersection W1 with W2 is the number of vectors is n. Dimension of W1 is n plus m, and dimension of W2 is n plus k. Now we prove that the system of vectors W1 up to Wn, this, and the vectors added here, V1 up to Vm, and the vectors added here, U1 up to UK. This is a basis, in W1 plus W2. Let us denote this start in B0 and this to be denoted by B. Evidently, W1 plus W2 is the span of this any element. From here is a sum, but x is a sum of these vectors, y is a sum of these vectors, so x plus y is a linear combination of these vectors. So we have this. It remains to prove that B is a linearly independent set. We prove that B is a linearly independent set. In order to obtain that B is, and if after we prove this, we get that B is a basis, and from this we get dimension of W1 plus W2 is N plus M plus K. This is exactly the sum of this minus N. So it remains to prove that we have a linearly independent, this is a linearly independent set. I shall write here. For this, we consider a linear combination of these vectors equals to 0, and we prove that all the coefficients must be 0. So let alpha 1 W1 plus up to alpha n Wn plus beta 1 V1 plus beta m Vm and plus gamma 1 U1 plus gamma k UK equals 0. So we have to prove that a linear combination of all these vectors can be 0 only in the case when all the coefficients are 0. Okay, this relation can be written as alpha 1 W1 plus alpha n Wn plus beta 1 V1 plus beta m Vm equals minus gamma 1 U1 minus so on minus gamma k UK. The vectors U are from W2, so this belongs to W2, and this is a linear combination of the vectors of the basis of the W1. So the two vectors are equal, so they belong to the intersection. From this we get that, let us consider, for example, this one. Okay, minus gamma 1 U1 minus gamma k UK belongs to W1 intersection W2. It is the same as this vector, and from this we get that it will be a linear combination of the vectors of the basis from here. From this we get that there exists delta j such that this vector minus gamma 1 u1 minus gamma k uk to be a linear combination of the vectors of the basis will be delta 1 w1 plus up to wn delta n wn. But this relation is equivalent to delta 1 w1 plus up to delta n wn and plus gamma 1 u1 plus so on plus gamma k uk equals 0. This equality, but the vectors from this relation are exactly the vectors of a basis from W2. So they are linearly independent and all these coefficients must be 0. Particularly for us, it is important that gamma 1 equals gamma 2 equals so on equals gamma k are 0. Up to now, we know that these are 0, and the relation number 1 becomes these are 0. It remains just alpha 1 w1 plus up to alpha n wn plus beta 1 v1 plus beta m vm equals 0. But these vectors form BW1 basis in W1. So this linear combination can be 0 only in the case when all the coefficients are 0. So we get that alpha 1 equals up alpha n equals beta 1 equals beta m, all are 0. So the considered system of vectors from W1 plus W2 form a basis, and we obtain the relation concerning the dimension. Now, the following result concerning the sum of two subspaces. Okay. Theorem. Any vector x from W1 plus W2 can be admits a unit can be written as x equals W1 plus W2 with W1 from on W can be written in just one way. This if and only if the intersection between the two spaces is the null space. Proof. Let us firstly prove this in this direction. It is necessary to have this intersection to contain only the null vector if there exists a vector letter, in W1 intersection W2 y different from 0, then our vector x equals W1 plus W2, but it also can be written as W1 plus y plus W2 minus y. This is from intersection, so this will be from W1, this belongs to W2. So if the intersection is not 0, then a vector can be decomposed in more than one way in this form. Now, this application. And now we assume that W1, the intersection, contains only the null vector, and let us consider that x can be written in two ways, W1 plus W2, and also as W1 prime plus W2 prime, with this from W1. From this relation can be written also this equality as W1 minus W1 prime equals W2 prime minus W. Okay, but this vector belongs to W1, this vector belongs to W2, but the intersection, so both are in intersection. If we also consider this relation, we get that this must be the null vector. This also, we get W1 minus W1 prime is 0. W2 minus W prime also is 0. So we get that such a decomposition is unique. Each vector from the sum can be decomposed in just one way. In this case, we say the definition. We say that the sum is a direct sum definition. We say that W1 plus W2 is a direct sum. And use the notation. W1, W2, if the intersection of the two subspaces is the null space. This is the direct sum, but also it is indicated that here we have a direct sum. Any vector can be written in just one way as the sum of a vector from this space and a vector from the other space. Another definition, we say that W2 is a complement of W1 in V if V is the direct sum W1 plus W2. Now, here we consider an interior sum of spaces, vector spaces, the case when both are subspace of a larger space V. Now, we can consider a more general case theorem. Let us write here. If V1, V2 are vector spaces over the same field K, are both real or both complex vector spaces, then we get that the vector space V1, that is in product, the set of vectors is this one. The addition is by components. That is the set of vectors of the form x1, x2 with x1 from V1, x2 from V2. And the addition x1, x2 plus y1, y2 equals x1 plus y1, x2 plus y2. And the multiplication with the scalar lambda x1, x2, multiplication also by component, lambda x1, lambda x2. This is a vector space over K, and dimension of this view is the sum dimension V1 plus dimension of V2. We have this relation. Proof. One can easily check the axioms and to prove that here we have a vector space. Now let us consider a basis if V1 containing the vectors V1 up to Vn basis in V1, V2, W1 up to Wk basis in V2, then we get that our vector space V1 times V2 described there. Each this is a vector from a V1, so will be a linear combination of this. An arbitrary vector from here has the form alpha 1 V1 plus up to alpha n Vn. The second component is a vector from W2, will be a linear combination of this beta 1 W1 plus beta k wk, where the coefficients alpha k, beta k are from the field of scalars. This can be written as alpha 1 v1 0 plus up to alpha n vn 0 plus beta 1 0 w1 plus so on plus up beta k 0 wk. So is the span of the set containing these vectors v1 0 up to vn 0 0 w1 0 wk, and this is a linearly independent set of vectors, linearly independent. So it is a basis, and you can see that the number of vectors is exactly dimension of v1 plus dimension of v2. We can identify v1 with a subspace of v2 also, and then this is exactly the sum of two subspaces. Can be identified after this identification. V is the sum of two subspaces, and we have a direct sum of two subspaces, but only after an identification. V1 can be identified with all the vectors of the form x0 with x from v1, and this is contained in v1 times v2, similarly v2, and then v is after this identification is the direct sum of the corresponding subspaces. Now, factor vector space. If we consider a subspace theorem, let W in V subspace, then first the relation x equivalent y if x minus y is in W is an equivalence relation in V, and we can decompose V in classes of equivalence. Now this is firstly now on the set of the classes of equivalence. We denote this in this way. V factorized by W is the set of the classes of equivalence. We shall prove that the class of X is just a translation of W is X plus W, where X from V. X is a representative. When X is from V, each class is obtained here several times. The addition, class of X plus class of Y, by definition, class of X plus Y, which are elements from V, so we have the addition, and the lambda times class of X is the class of lambda X. This set, the elements are also sets with this addition, vector addition, and scalar multiplication is a vector space called factor space, vector space, quotient vector space, and third, the dimension of the vector space obtained in this way is the dimension of V minus dimension of W. Now, firstly, the description of the classes of equivalence. By definition, the class of X is the set of all the vectors Y from V such that Y is equivalent to X equals vectors Y from V such that this means the difference Y minus X is in W. Set of Y from V. This can be written Y is belongs to the vectors having the form X plus W. So all the vectors having which belongs to this set, so is X plus W. Indeed, the class of X is just a translation, and here is the addition. For example, the class of X is 0 plus W, which is just W. This is the null vector in this space. And here is the addition. You can remark that W plus W, the sum of two spaces is exactly W, and the class of X, which plus class of 0 means X plus W is X plus W. So is the class of X. So this is indeed the null vector in this vector space. It is one can easily check the axioms and obtain that in this way we get a vector space. Now the dimension for this. We consider a basis in the subspace W and extend it up to a basis of V. I shall let be containing the vectors W1 up to Wn basis in V. In W, we extend we extend B up to a basis of V, namely this is W, B, W1, Wn, and we add other vectors V1 up to Vk basis in V, and we prove that the set here is a basis in V, that B containing the class of V1, so on, class of Vk. This is a basis. This is a basis in V over W. My laptop is sleeping. We prove that, okay. For this, we have to prove that V over W is the span of B. An arbitrary element V over W is the set of classes for X from V equals a class, a basis in V is here. So here is the class of instead of X will be a linear combination of this alpha 1 W1 plus alpha n Wn plus beta 1 V1 plus beta k Vk, where the coefficient alpha k, beta k are from the field of scalars. And now by using the definition of the addition of scalar multiplication, this can be written as alpha 1 plus of W1 plus alpha n plus of Wn plus beta 1 plus of V1 plus beta k plus of Vk, where alpha k, beta k are from the field of scalars, but the class of W1, class of W1 is W1 plus the subspace W, but this is an element here, so is just W, so is 0, class of 0, class of 0, class of 0, and so we get that this is span, a linear combination only of class of V1 up to class of Vk. Now it remains to prove that this set of vectors is linearly independent. For this, we consider a linear combination equal to 0. Let gamma 1, let lambda 1 V plus V1 plus lambda k plus Vk equals class of 0. We have to prove that the coefficients must be 0. This can also be written as the class of, by using the vector addition scalar multiplication in our vector space, lambda 1 V1 plus lambda k vk. This class is the class of 0. So from this we get lambda 1 v1 plus lambda k vk belongs to w. So we get that lambda 1 v1 plus lambda k vk will be a linear combination. This is the basis in W will be that alpha W1 plus up to alpha alpha n Wn, and this relation can also be written as alpha. From this we get alpha W1 plus alpha 1, alpha n Wn minus lambda 1 v1 minus lambda k vk 0. But the vectors from this relation form a basis in V, the basis. We get that all the coefficients must be 0, particularly lambda 1 equals lambda 2 equals so on equals lambda n. So this the considered these are linearly independent and they this is a basis in our space. So the dimension of this dimension of V out over W is we have obtained that the dimension is k. Dimension of V is m plus k. The dimension of W is n. So this is just the difference. An example time 1 hour. An example in R3. In R3 W, we consider the space of 0, 0, gamma real. This is a subspace in R3, and so R3 if we factorize by this, these are the classes of equivalence. We obtain this vector space if we do not take into consideration the third component. Let us see this. This will be x, y, z plus w. Our description y, x, y, z R3. And you can see that if we add this, we get the elements of the form xy. Okay. We get that the class of z, this is the class of yz, contains all the elements of R3 having the form, and here an arbitrary alpha, where alpha belongs to. And xy are here we add the set all this set. So on the first position we have xy, and this is an arbitrary. So by using this subspace, this is W, is this subspace, and the other, for example, if here is x 0, xy 0, then this is the class. This is a representative of this. We can identify this R3 over W, identify R2, this if for each class we consider the intersection here. You can investigate the addition, multiplication, linear independence, basis in this case. Thank you very much.